While studying the EM wave propagation, particularly while deriving the wave equations, you must have heard about the concepts Helmholtz equations. We had vector Helmholtz equations as well as scalar Helmholtz equations. And most of the students get confused between these two terms, vector Helmholtz equations and scalar Helmholtz equations. So in this video, let's see what is exactly the difference between these two equations. When we start learning electromagnetic wave propagation, EM wave propagation, the very first thing that we do is the derivation for EM wave equations. Yes or no? Starting from the Maxwell's equation, step by step, we do derivation to ultimately reach up to the wave equations. Am I right? For deriving EM wave equations, we start with Maxwell's equation. As you can see from the screen, this is the set of Maxwell's equations. And for simplicity, we generally assume the free space as our medium. So this is the set of Maxwell's equation for the medium free space. So starting with these equations, what do we do then? We simplify these equations to get the Helmholtz equation. Then we solve that Helmholtz equations to get our wave equations. Am I right? So I am not taking complete derivation over here. I am just pointing out the difference between the vector Helmholtz equation and the scalar Helmholtz equations. Okay, so starting with these equations, what do we do next? We simplify those equations. How do we simplify? We take curl of both the side of either equation, del cross E equation or del cross H equation. Yes or no? If you start with del cross E equation, you will get the wave equation for E, later you get the equation of H. Otherwise, if you start with del cross H equation, first you will get the wave equation for H, then you will get the equation of E. So whatever, you perform the curl operation on both the side of any one of these equations, and using these Maxwell's equation, we simplify that step. We apply the vector identity, yes or no, and using that vector identity, we simplify those things, and as you can see from the screen, we finally get that equation del cross E equal to minus beta square E. Yes or no? We take that constant omega square mu 0 epsilon 0 as the beta square propagation constant. So whatever, that is not the point of discussion over here. But after simplifying these Maxwell's equation in very first stage, we get the equation like this, del cross E vector. And of course, we use the Maxwell's equation in their phasor forms. Yes or no? As you can see from the screen, for every field vector, there is written small s in their foot. Yes or no? So that small s is for phasor representation. We derive the wave equations. For deriving the wave equations, we use equations in their phasor forms. So that S is for phasor representation. And you must be known with what is the phasor representation. So in very first stage, when you simplify the Maxwell's equation, we get this equation del square E vector in its phasor form, ES, or I will say just E. So del square E equal to minus beta square E, and this equation is nothing but your vector Helmholtz equation. So this equation is your vector Helmholtz equation. Del square of vector field E equal to minus beta square vector field E, and of course that subscript S is for the phasor representation, as I have just told you. Okay, so this is your vector Helmholtz equation. And can you observe very peculiar characteristics of this vector Helmholtz equation? Can you observe it? Can you see the very important thing present in this vector Helmholtz equation? See, del square, that means del square is nothing but the Laplacian operator. Yes or no? So del square of vector field E, the Laplacian operator is applied over the vector field. The del square operator is applied over the vector field. After simplification, what did we get? The del square operator, Laplacian operator, is operating on the vector field, and this point, and this is its peculiarity. You know that del square or Laplacian operator, it operates on the scalar field. Yes or no? Del square operator, del square del x square plus del square del y square, double derivative with respect to x, double derivative with respect to y. So that del square operator, if you remember, it operates on the scalar fields. But what you can observe over here, del square operator is operating, Laplacian operator is operating on the vector field. So this is very peculiar thing about this vector Helmholtz equation. Next, after getting this vector Helmholtz equation, then what do we do? What do we do in our derivation? If you remember, we write this vector field E in terms of its constituent components, x component, y component, z component, as you can see from the screen. Yes or no? We write this vector field E in terms of its constituent components. And my dear, after that, we compare both the sides of the equation and we compare the coefficients of unit vector Ax, the coefficients of unit vector Ay, and coefficient of unit vector Az. And if you remember, as you can see from the screen, we get three equations, like as you can see from the screen, del square Ex, of course in the phasor form, del square Ex equal to minus beta square Ex. One equation for x component of E, one equation for y component of E, and similar equation for z component of E. Now my dear, all these three equations, they are looking exactly similar like the vector Helmholtz equations, but these equations are known as scalar Helmholtz equations, one for each component of E, and these are scalar equations. Yes or no? We have just compared the coefficients of unit vectors. We didn't consider complete vector here. The complete vector field E is present in the vector Helmholtz equation. But in the scalar Helmholtz equations, only coefficients, that x component, y component and z component without the unit vectors, that are only present. So these are scalar equations, and these three equations, these are known as scalar Helmholtz equations. Am I right? Then after that, in the derivation, we solve these scalar Helmholtz equations. We operate with del square. Del square is your Laplacian square. Double derivative of x plus double derivative of y. We go on solving. We get the differential equation, and after solving that, finally we get the wave equations. So that is not the point of discussion over here, but whatever point was, the vector Helmholtz equation, in the vector Helmholtz equation, the del square operator, it is operated on the vector field E, and in the scalar Helmholtz equation, the del square operator is operated on the individual component, scalar function, individual x component, y component or z component of E. Okay, and one vector Helmholtz equation gave us three scalar Helmholtz equations. Yes or no? One vector Helmholtz equation gave us three scalar Helmholtz equation, one for each component. Later on, we discussed that z component, if your wave is traveling in the z direction, that is the next story. But the vector Helmholtz equation, the single vector Helmholtz equation, gives us three scalar Helmholtz equation, one for each component. So my dear, this is the difference between vector and scalar Helmholtz equations. In the next week, let us come up with another mind-bending concept. Thank you.